Hello, everyone. Hope everyone is doing well so far. So today I'm going to be going over number 2 of homework. So for this problem, you're essentially what you're trying to do is try to find the variance-covariance matrix for the p plus 1 by 1 vector beta hat for the least squares estimate, which is given by variance of beta hat equals sigma squared times the inverse of x transpose times x. And you're trying to derive the 2 by 2 variance covariance matrix for least squares estimates for simple linear regression. So you're trying to figure out this, get the results, so that way you get this matrix right here. And what else? All right, and so that's kind of what the problem is asking. And let's get started. So for that problem, you want to recall from week 7 lecture that the definition of the X matrix when you're given a simple linear regression or just a regression in general is X equals this matrix where you have a row of 1, x11, x12, all the way to x1p, with p referring to the number of predictors in your model. And there are n rows and p plus 1 columns for just regression in general, especially for the definition of the X matrix. However, in this problem, we're talking about simple linear regression. So an equation that's something like this, y, hold on, oops. So y equals beta naught plus beta 1x plus e, meaning the error. And so you see here, this is essentially the equation of a line. And in this situation, our p would be 1 because there's only one predictor in this model, since this question is asking specifically for simple linear regression. So because p is 1, that means our dimensions for our X matrix would actually be n by p plus 1, or essentially 1 plus 1, which gives our dimensions to be n by 2, which means that we will only have 2 columns. So once you figure that out, it will essentially be this. So first column, second column, we just have this part right here. I'm not sure if you all could see. So just right up to here. Yeah, that would be for simple linear regression, just a matrix defined up to here. So for this situation, X will be defined by an n by 2 matrix, with n being the number of X values or observations in your data set. So our matrix X would be defined by basically one column full of n number of ones for the entries in the first column. And then the second column are essentially a listing of all the X values for your data set, for the population, ideally. So from x1, x2, all the way to xn. And then for the sake of this problem, let's also define the transpose of X, or X with the apostrophe, X prime, if that's the right way to call it. So X, the transpose of X, would then be defined where you essentially switch the rows into columns, columns into rows. So X transpose would then be defined as a row of ones, and then the next row are essentially a row of X values from 1 to all the way to n, number of them. So now that we define these two, let's go back to the problem. So in this problem that you have, they give you, the variance of beta hat, which is equal to sigma squared times the inverse of X transpose times X, right? Right here, we just define what X and X transpose is for a simple linear regression model. So using this definition, let's plug in X and X transpose as we defined up here. So this stuff right here, plug it in for X transpose and X. So plug that in here. So down here and down here. down here. Yeah. So you plug in X and X transpose as defined here into the equation for the variance of beta hat. And remember that sigma square is a constant. So once you plug in X transpose and X, you will get essentially sigma square times the inverse of X transpose, which is essentially a row of ones, and then the next row being listing of all the X values from 1 to all the way to Xn, and then essentially X itself, which is a column of ones and a column of all the X values from X1 to Xn. All right. So now that you've plugged in the definitions for X transpose and X, you want to evaluate this matrix multiplication. So since X transpose is 2 by n, and then X itself is n by 2, the dimensions agree, the inner dimensions agree, so the resulting matrix would be 2 by 2. So to start off, to get the since our resulting matrix is 2 by 2, let's figure out the elements for this 2 by 2 matrix. So for the first element in the first row, first column, you would want to take this first row of X transpose and multiply it with the first column of X. So you take each element in a row and you multiply it with the column element in this other matrix. So if you keep doing that, you'll essentially find it's just 1 times 1 plus 1 times 1, an n number of times. So which will get you this summation where you go from I equals to 1 to n 1 square. And you do that n number of times. And if you know, 1 times itself is just 1. So, and you're adding up a bunch of ones n number of times, which will get you essentially n, pretty much. All right, that's for the first element in the first row, first column of this matrix. That's done. Now for the second element, for first row, second column, you do the same thing, except for X, you multiply this first row of X transpose with the second column of X. So 1 times X1, 1 times X2, all the way to 1 times Xn. Essentially, once you figure out the multiplication here, the dot product, essentially, you'll find that essentially you're just adding up all the X values, which gets you this nice summation from I equals to 1 to n for xi, this summation right here. Now you just do the same thing, but with the second row and then the first column, the second column respectively. So x1 times 1 plus x2 times 1 all the way to xn plus 1 gets you essentially, again, a summation of all the X values, which is essentially I equals to 1 to n for xi, this summation right here. And then for this last element right here, essentially you have each X value and you multiply by itself, and then you add up all the sum of the square of each X value. So x1 times x1 plus x2 times x2 all the way to xn times xn. A summation of all the square of the X values will get you the summation from I equals to 1 to n for the square of xi. So there you have it, is the matrix multiplication of X transpose times X. And so the result, hold on one second, let me zoom out a little bit. So the result would be sigma squared times the inverse of this matrix right here. You have n, sum of the X values, sum of the X values, and sum of the square of the X values. But we're not done yet here. We also gotta take the inverse. Now, if you remember from lecture earlier about doing the inverse of a 2 by 2 matrix, you know that given a matrix with A that's 2 by 2 with elements A, B, C, D, the inverse of A would be 1 over the determinant of A times this matrix here where you have in the first row D and negative B, and then the second row negative C and A. Essentially, you just switch the positions of certain elements, and then you change the sign of the diagonal going from right to left. Equals to, and then for the determinant, which it's just equal to 1, is just equal to AD minus BC. So using this definition of the inverse of a 2 by 2 matrix A, use that to then evaluate the inverse of this matrix in here. So doing that, essentially what happens here is you switch the positions of n and the sum of the square of the x values here. So this one goes where n is, and then n goes where the sum of the square of the x values are. And then for here, you just add a negative number here and then -1 here. And then when you evaluate that, you get essentially this result right here. And then for the determinant, once you evaluate this using just this definition of A inverse here, you get the denominator, which is n times the sum of the square of the x values minus the square of the sum of the x values right here for the denominator of this constant right here. All right. So this is what we're going to get for the variance of beta hat so far. However, you can rewrite this actually using the definition of the mean of the x values. And if you all remember from your previous stats classes, you know that the mean of the x values, or x bar, is equal to the sum of all the x values divided by the total number of observations. In this case, the total number of observations being represented by n, right? So you have this formula right here. Now, if we rewrite this, if you multiply both sides by n, you get that the sum of the x values is equal to the number of observations times the mean of the x values, x bar, in other words. And using this definition, you go back here and you notice that we have the sum of the x values here. So using this new definition of the sum of the x values, you want to substitute that definition wherever the sum of the x values are. So use this definition, and then you plug it in to, say, you plug it into here where the denominator is, and then you plug it into, just plug it into here, just here, all right? And just for the denominator, and you'll get that you have the square of n times the x bar, right? And then when you evaluate that, you'll get n times sum of the square of the x values minus n squared times x bar square, right? And then once you simplify it a little bit more here, remember that in the problem, you're given this identity, which is the sum of the difference between x value and x bar square, sum of all of those differences, is equal to sum of the square of the x values minus n times the square of x bar. And using this identity right here, which I rewrote here for convenience, you can rewrite the denominator here below the sigma square. So you can rewrite this after you factor out n, 1n, and once you do all the rewriting, applying this identity to this denominator and substituting it in, you'll get that the denominator under sigma square is n times the sum of the difference between xi minus x bar, and then the square of that difference, and the sum of all those square differences. So that's kind of what you get here. So this is still, we haven't done anything yet, but this is what we got so far. Alrighty. After that, you take this constant and then you distribute it to each element in this matrix. So sigma squares over n times the sum of the squared differences for x will get you this right here. All right. So hope you all can follow the math here. I'm going a little bit fast, so bear with me. All right. And then you do some simplification, cancel out the ends wherever you can. And then once you do some simplification, do remember that definition we had for the sum of the x values being equal to n times x bar. Remember that that definition we found earlier? You're going to use that again to do some more simplification. To simplify, let's see here. Yeah, you do a little bit more simplification here. So wherever you see the sum of the x values, you want to substitute it with n times x bar. As when you do that, you'll cancel out the n on the denominator. So this here, the n's cancel out. So now, once you do that simplification, do remember from the problem that you're given that sxx is equal to sum of the differences between xi and x bar, and each difference being squared. So just for simplicity's sake, we're going to rewrite this as xxx. So wherever you see this sum of the squared difference between x and x bar, you want to replace it with sxx, right? Just for convenience, though. And if you want to rewrite a little bit further, remember that definition identity that we used earlier? This one right here? This one? You see here? Remember, so once you see that identity that the problem gives you, well, it turns out you can actually rewrite it to get the definition for the sum of the square of the x values. And one way to do that is to add an x bar square to both sides right here. So you get, the sum of xi squared, all the xi squares equal to sxx plus n times x bar squared. And use this definition right here to substitute for sum of the square of the x values. And you plug that into the element in the first column, first row, wherever you see the sum of the square of the x values. And you'll get this equation here where you can then distribute the constant right here, sigma squared over n times sxx. You distribute it and you do some simplification, cancel out the n and sxx wherever appropriate. And you'll find that once you do some simplification, you will find that you'll get the definition for the variance of beta naught hat right here. And you can even compare it to the problem description too, as they tell you what variance of beta naught hat is. So doing the comparison, you see they match up. So you pretty much prove that you'll get the variance of beta naught hat in the first column, first row of this 2x2 variance covariance matrix. So you got that. Similarly, you'll get the same thing for this element in the second row and second column, sigma squared over sxx, which is the definition of variance beta 1 hat, which is also pointed out in the problem description. So with that said, you pretty much have shown that variance beta naught hat and variance beta 1 hat is given by the variance covariance matrix. So you pretty much got these two elements here. Now, for covariance of beta 1 hat and then beta, hold on a second. Let me, oh yeah. For beta 0 hat and getting this, I know there's some complex algebra that you got to do, but it's not needed for this problem. But notice how these two are the same thing. As if you guys remember from stat 620, the definition of covariance doesn't change depending on the way you order the pair of what is it? I think random variables. So here you can just put in covariance beta 0 hat, beta 1 hat, and then covariance beta 1 hat and beta 0 hat. And so that's pretty much it. You pretty much have proof that you've gotten the variance covariance matrix from just tinkering with the definition of variance beta hat. I know that it's a bit complicated a little bit, but I hope you all can follow and understand where this is coming from. Now, this is pretty much the end of this video, but if you want to know where this covariance is coming from, while it's not entirely necessary for this problem, I thought it would be nice to really cover where this covariance stuff come from. Like, how do you pretty much show these two? So remember from stat 620 that the covariance of two random variables is pretty much the order doesn't matter. So covariance of beta 1 hat, beta 0 hat is equal to covariance beta 0 hat and beta 1 hat. And additionally, remember from, I guess, your probability class that the definition of covariance xy is equal to the expectation of x times y minus expectation of x times the expectation of y. And if you write it, you pretty much get the same thing, but just the different ordering of variables. So covariance xy or covariant yx are both equal. So essentially the same thing. So that means covariance of beta 1 hat, beta 0 hat is equal to covariance beta 0 hat and beta 1 hat. But for just simplicity's sake, let's just start solving covariance beta 0 hat and beta 1 hat. So using the definition of covariance up here, we're going to figure out covariance of beta 0 hat and beta 1 hat, which is the expectation of beta 0 hat times beta 1 hat minus expectation beta 0 hat times expectation of beta 1 hat. Now, you want to remember from lecture 2 that beta 0 hat is defined as equal to y bar minus beta 1 hat times x bar. So using that definition of beta 0 hat, you substitute that for beta 0 hat. So wherever you see beta 0 hat, you want to substitute with this equation right here. All right. So once you do that, then you want to distribute this beta 1 hat for this first term, right? And you get this right here. And then using properties of expectation, you can separate this equation here into two separate expectations. So this expectation here, you can split it into two, right? And then by the property of expectations, you can pull out constants and the constant won't be affected. So remember that y bar and x bar are constants. You know, they're fixed numbers. So you can pull them out of the expectations, right? And hold on a second. Yeah, you can pull them out and then distribute this expectation of beta 1 hat onto each of these terms. And once you do some simplification, you will find that expectation of y bar times beta 1 hat cancels out with this term y bar times expectation of beta 1 hat. So that cancels out to 0. And then once you bring down all these terms, you will get minus x bar times expectation of beta 1 hat plus x bar times the square of expectation of beta 1 hat. Now, if you factor out the negative x bar, you will find that you'll get expectation of beta 1 hat minus the square of expectation of beta 1 hat beta 1 hat, sorry. Now, if you remember from probability theory, this is the definition of variance. As if you recall, the variance of a random variable, let's say x, variance of x, is equal to the expectation of x squared minus the square of expectation of x. So using that definition, you can rewrite this to be the variance of beta 1 hat. So you get that covariance for this problem is equal to negative x bar times variance of beta 1 hat. And then plug in the definition of variance beta 1 hat, which we found earlier, you'll get that the covariance is equal to negative x bar times sigma square over sxx, which matches up with what we got in this variance covariance matrix we kind of shown earlier, we solved earlier. So thus, you pretty much have proven that the variance of beta hat is equal to this matrix, this 2x2 matrix, where you have variance of beta 0 hat, covariance beta 0 hat, and beta 1 hat, and then the covariance of beta 1 hat and beta 0 hat, as well as variance of beta 1 hat. So for that said, hope you all really enjoyed this video. Hope you find this video very helpful. If you guys got any questions, feel free to ask me. I'll try to walk through it. And I know it's a little bit hard to try to do it over video, especially with the small screen that I have, but hopefully it's helpful nevertheless. So anyway, thank you all for so much and have a great day. Take care.